So dense correspondences between any two images. This is joint work with my student Moria from the Open University of Israel, sitting up there. The problem of dense correspondence estimation is the problem of matching all the pixels in one image to pixels of another image. For the majority of the history of computer vision, this is mostly meant trying to match pixels based on their intensities, using things like the assumption of brightness constancy in applications such as stereo vision. So you have two images of the same scene, and the same scene assumption is very strong here. And you're trying to match pixels on, say, the left image to pixels on the right image, which have the same intensities or the same local intensity patterns. And then you want to reason about their displacements and say something about the structure, the 3D structure of the scene that you're seeing in these two images. About 10 years ago, people started looking beyond this brightness constancy assumption, looking to more general scenarios where you're not matching intensities necessarily, but trying to match things which have similar semantic content. So just to give an example, consider these two images. They are very obviously not the same scene anymore like they were in the previous example, but very obviously they share the same semantic content. I mean, you're seeing road in both of them, you're seeing cars, you're seeing buildings, and you're seeing skies. So it makes sense that you should possibly be able to match pixels that are on the buildings on the left image to pixels that are on the buildings on the right image. It doesn't just make sense, it's actually quite useful to do so, because if someone went to the trouble of labeling per pixel the right image, telling us which pixels were the sky, which pixels are the road, which pixels are the buildings, and so on. Once you've established these dense correspondences, you can borrow these labels and assign them to the pixels on the left image, helping you to reason about the contents of that image. So over the years, this has been called scene labeling or scene parsing, and people have done this successfully in the past. I think these two images I've shown here in my very first talk here at the IBC Vision Day almost 10 years ago. In this particular example, again, you're seeing two images of two different scenes, but again, the same semantic content. You're seeing a person in both of them. Now, let's say that someone provided us with a depth map for the image on the right, so that's the distance from the camera to the surface of the object appearing in that image at each and every pixel. Once you've established dense correspondences, you can borrow these depths and use them to estimate the shape of the object appearing on the left image, rendered here as a surface and not a depth map. Over the years, this has been called depth transfer, and several people picked it up, and it's a very useful way of trying to infer structure from a single view. People have used dense correspondences for recognition. People used it for new synthesis, for processing challenging images of ancient texts, and many other applications. So just to summarize this short introduction, dense correspondences are an extremely useful tool in computer vision, provided that first, you can compute them efficiently enough for you to be able to use your dense correspondence estimation method within a larger computer vision framework. Accurate, many of the applications that I've shown require per pixel labels to be transferred from one image to the next, so you need per pixel accuracy. But possibly the most important is robust. And when I say robust here, in all the applications that I mentioned, other than stereo vision, robustness refers, amongst others, to the ability to tie pixels across scene differences. So different scenes, and you're still robust enough to match pixels which share the same semantic content. So how do you perform cross-scene correspondences? There are many ways of doing it, but sort of the key to doing this successfully, one of the keys to doing this successfully is by using a robust per pixel representation. And one of the popular representations that people have been using in this context is the dense SIFT, the dense scale invariant feature transform. So the dense SIFT takes an image such as this and transforms it into a volume that looks like this, where each pixel is converted into a vector of 128 dimension, 128 floating point values, which is the SIFT descriptor extracted at that particular pixel. So we have a SIFT per pixel. Now, as you all know, SI in the SIFT stands for scale invariant. Now, the SIFT itself, the descriptor itself, is not scale invariant. no matter what they tell you. SIFT is scale invariant only because of the detector that's used prior to extracting the SIFT, a detector which selects the scale or the spatial support that's used to extract the SIFT. So it chooses a radii around each particular point, which is used to extract the descriptor itself. Now, this isn't an arbitrary decision or selection. The scale is selected in a way which is supposed to be repeatable across different images of the same scene. So you would get the same visual information processed and converted into a descriptor, no matter what the scale of the images is in practice. And of course, we know how to do this. I mean, there's since David Lowe's work in 2000, there is the dog-based and the log-based scale selection functions. And if we take this image over here and stick it into an off-the-shelf feature detector, this is what you'll get. So these are the detections, and the scales at each detection are visualized as the radius of the circles around the different points. And this works quite well. I mean, everybody's been using this for 15 years now. But the problem with this is that even for a very, very textured, busy image like the flower image that you've seen here, only about 0.5% of the pixels actually end up with scale selections for them, scale selected for them. And the reason this happens is because the other 99 or so percent of the pixels, on average it's about 99%, don't have enough local visual information around them for the scale selection function to be able to determine a scale in a way which would ensure this repeatability that I mentioned earlier. So how do you extract dense SIFT for all the pixels in the image when you only have 0.5% of the pixels with scales? That's very simple. You forget about the SI and just use a single user-selected constant scale for all pixels. Something that would look like this. Now, this works quite well in practice, and many people have used it for many different applications, but it's easy to show, and many people have shown, that this doesn't really work well if your scenes, if your two images have scale variations in them, and things appear in different scales. I mean, even in this very simple scenario that you're seeing here, these very simple two images, the same scene, and everything's pretty much the same scale, the fact that the car moved forward from one image to the next, if we're extracting SIFTs at the same scales, that would mean that we're comparing different visual information, apples to oranges, from one image to the next. So the comparison would not be, the SIFTs will not be comparable, and you probably get wrong matches and wrong flow. Okay, so how do you handle scales between two images? One way is to say, well, the hell with it. SIFT flow works well, let's just continue with it. It works for many applications. In some cases, you don't actually need scale if you have enough images in your database and they're all scaled correctly, or you're guaranteed to find one which is in the proper scale. So you can use dense SIFT. Another approach would be to use a multi-scale representation. Now, multi-scale representations are descriptors which were designed to pack into them information from multiple scales and allow this information to be effectively compared between different descriptors. So, two such examples are the scale invariant descriptors, the SID descriptors of Kokinos and Youth in 2008, and the scalar SIFTs of these guys over here, Talit Al, the scalar SIFT from 2012. Now, these two methods work much better than the original dense SIFT in terms of accuracy, especially when you have scale differences between the two images, where dense SIFT fails completely, and these work quite well. But this ability comes at a price. You remember I mentioned that dense SIFT is 128 dimensions, SID is 3,000 dimensions. Now, the SLS, I won't write this down because it's a big number, but it's a pretty big descriptor. It actually works well with PCA, as we've shown, and could be reduced down to 500 dimensions. But it's still much larger than the original dense SIFT and still requires much more effort to extract than a simple dense SIFT descriptor. And all this effort goes into the descriptor just in order to capture information from multiple scales. So that seems like an awful lot of effort just to capture information that appears in multiple scales and bridge across scale differences. And just if that wasn't clear, that's per pixel. So even a small image could end up blowing up into gigabytes of information. So in this work here, what we propose is a method for dense correspondence estimation between two images which portray different scenes, possibly different scenes, and possibly different scales. But we want to do this with the same price tag as the original dense SIFT descriptor, the original effort and space that's required to match pixels using, match images using dense SIFT. And we do this with scale propagation. Now the idea here is pretty simple. The idea follows the observation that similar pixels should typically imply similar scales. If you take this image, for example, and run your off-the-shelf garden variety feature detector to detect scales, you'll get something like this. And again, the radii of the circles reflects the scale at each one of these points. And again, despite the lots of green that you're seeing here, only about 0.5% of the pixels were actually selected by the feature transform, by the feature detector, I'm sorry. So let's just zoom into one region of this image, and let's say that we found detection here, and this circle's the size of the circle, the radius of this circle reflects its scale. So what we're essentially saying is that the pixel immediately to the left of it and to the right of it could actually use the same scale. There's not much difference between these two images, so why not share the scale that we've detected in the original feature point? In other words, why not take the scale that we detected in that feature point and propagate it outward to the pixels around it? And if we have another feature point somewhere else, propagate its scale, and another feature point, propagate its scale, in a way which would allow all the pixels, which would provide all the pixels in the image with scale assignments. This scale propagation is performed by defining a global cost function for scale assignments, which looks something like this. Anybody who's familiar with normalized cuts with, I don't see Anat Levine here, but image colorization, any of the scribble-based techniques for image modification or editing, all of these know or are familiar with this sort of equations. Essentially what it means is that the scale of each pixel P should be as close as possible to the weighted average of its neighbors, Q, immediate neighborhood. This, of course, constrained by the pixels that we do have scales for, that 0.5% of the pixels for which we do, in fact, have scales. Now, if we take this, we can convert it into a large sparse system of quadratic equations, and this could be easily solved with built-in MATLAB operators. So this is extremely efficient to solve and extremely efficient to propagate the scales. So there's a lot to be said about the weights that we're using, but I won't go into these details, and instead just cover the entire pipeline. Given a pair of input images, and in this case, two images of the same scene, but with very obvious scale differences between them, we start off by running your off-the-shelf David Lowe SIFT detector descriptor combo. And then as the next step, we try to match the descriptors that we extracted in these sparse interest points in order to end up with a subset of the features in each one of the images, which we can reasonably assume are in common, are shared by both images. So we're only using the interest points, the feature detections that we can match across the two images. These feature points, we then feed their scales into our scale propagation routine and end up with this. Now, this, as far as I'm concerned, is the most important images of this whole presentation. What you're seeing here are the scale maps, the scale assignments for all the pixels in both these images. Color-coded, where warmer, redder colors are larger scales, and bluer, colder colors are smaller scales. And just by looking at these two images, you can learn three things. First, all the pixels in the images have scales, which is nice. Two, these scales vary from one pixel to another, so we're no longer talking about the constant user-selected scale scenario that we had for the original dense SIFT. And three, which for me was the biggest surprise and the nicest thing in this, is that if you look at these two images, scale assignments seem to be repeatable from one image to the next. Regions of low scales in one image corresponds to regions of low scale in the other image. For example, the wheel here of the trailer behind the bicycle is low scales in both images, but large scales in the region above it in both images. And this would imply that you're using matching scales to extract information from corresponding positions in the two images, which would mean that you have comparable sifts that would be hopefully easy to match from one image to the next. Now, once you have this, you can again extract your dense sift descriptors, but this time they're truly dense, they're truly scale invariant dense sifts, not the uniform diffs that we had earlier, the sifts without the SI that we had earlier. And once you have that, you can take your two volumes, dense sift, your two descriptor volumes, and stick them into your favorite matching engine. In all the examples that I'll show in our work, we use the sift flow, which was just convenient, but you can use other matching engines instead. Sift flow of Sylvia Gal from 2008 and 11. So some results, image hallucinations, just they're qualitative, but they look good, I think. So you have source and target images, and I hope you can see that these two images are, first, different scenes, two, different scales, and three, large homogeneous regions where you don't have interest points anywhere, or you don't even have information to determine scale reasonably, reliably. And we're comparing DSIFT, SID, SLS, and our own matching technique that I've shown earlier. Of course, following the extraction of the descriptors, the actual matching of the pixels is performed with SIFT flow. So the object of this game here is we want to form correspondences from the source to the target image, and then pull back the intensities from the target image onto the source, warping it into the shape of the source. So this is what we get for the different descriptors. I was hoping for a larger screen, so maybe I miscalculated. I hope you can see this well. There's some small errors on the side of the mouth, but otherwise, maybe this is wishful thinking on my part, but it looks like it took the Caucasian, very Caucasian-looking target image and Obama-fied it and made it look much more African-American than used to, warping it into the shape of the source. A couple of puppies, again, homogeneous regions, different scenes, different scales. We work about as well, I don't know if you can see this very well, but we work about as well as the SLS, but of course with a much smaller price tag in terms of both complexity and space. The real moon landing astronaut versus the Lego version of the moon landing astronaut. So again, I hope you understand these are different scenes. I'm not saying that we're perfect. We have some errors here and there, but generally speaking, we were able to twist and warp the real astronaut into the shape of the Lego, just where the other three methods failed. Again, two images, different scenes, same semantic content, different scales, large homogeneous regions, but all in all, I think we performed the best. The last example here, these two images are from the same scene, but in this case, the two images are of extremely different scales. One of them is much closer than the other. So this example is just to show how dense SIFT completely falls apart when you try to apply it to such cases. It's not designed to compensate over large scale differences, and then you get this rubbish here. The SID, SLS, and our own perform comparably well, but again, our results were obtained with much less computational effort. Quantitative results, remember all these applications that I mentioned earlier? So we made an effort to methodically test the influence of scale propagation in each one of these applications, and basically, in all cases, I won't go into the numbers, we were state of the art. That's not strictly true, actually. We did come a close second in some cases, but in every time that we came a close second, the first place was one of the huge descriptors, the SID or the SLS, So we lost a bit of performance, but we gained a huge amount, an order of magnitude in terms of both storage and processing power. So I'll wrap this up with a take-home message. Dense correspondences are good for you. Eat them with your greens every night. Local scales are not so local, so you can propagate scales. As far as I know, we're the first to try to do this, and it works. Efficient dense correspondences across scenes and scales is just one last qualitative result that I'm showing here. We do have code available online on our webpage with special thanks to Anat Levine's, whose colorization code formed the basis for our own code. I should wrap up, but before I do and before I take answers, I just want to plug in a different project altogether, just say a word about the fact that there's code online. So I'm not talking about the actual project, just showing these results and saying that there is code that you can download right now for our face frontalization project. So this is a different project completely, not related, completely unrelated to what I've talked about so far, but we have faces. You stick the faces into a function, and you get the faces facing forward, and we showed that this provides state-of-the-art results on the LFW benchmark. So you can get the code online from there too. So that's it for me.